10 years ago, databases were much simpler. Most companies would only have one or two types of databases in production. Today, the age of one-size-fits-all is over. Companies have multiple databases to deal with all of the different types of use cases, and databases have become distributed to multiple nodes in order to be scalable. Ozgun Erdogan of Citus Data joins the show today to give us a modern look at databases. Ozgun suggests that PostgreSQL alone can perform most of the work that we are trying to get from our variety of databases. We discuss how Citus Data scales Postgres, and Ozgun contrasts an all-Postgres architecture with other types of databases, such as the NewSQL class of databases, such as MemSQL and VoltDB. If you enjoy today's episode about databases, please share it on Twitter or Facebook, or tell your friends, when you're at coffee, about Software Engineering Daily or your favorite episode. It really helps the show grow. I think that it's strange because there's not really a way that people share podcasts with each other. Word of mouth really seems to be the only way. So you can also send me an email at softwareengineeringdaily@gmail.com. I'm always looking for new show ideas, and I would love to just get a message from you saying hi or saying when you listen to the show or what you hate about the show. Thanks for listening, and I hope to hear from you soon. Now let's get on with the show. I had a crazy idea a couple weeks ago. It's a photo sharing app that only has pictures of cats. When I finish my photo sharing cat application, I will be deploying it to Linode, because Linode is the fastest hosted Linux provider. I don't want to get locked into a proprietary platform that's going to overcharge me as soon as my app gets popular. I just want a fast Linux server with simple pricing. Go to linode.com/sedaily and get $20 in free credit today. Plans start at $10 a month, so my free $20 will be plenty to launch my cat photo sharing app. Once I need to scale, I can use tools like node balancers and backups, and Linode has built-in dashboarding and metrics so that I can see the traffic to my Linode servers, and I can understand how many of my users are posting cat pictures and looking at each other's cat pictures. Go to linode.com/sedaily and get $20 in free credit today. The plans start at $10 a month, so it's a great deal. Thanks to Linode for sponsoring Software Engineering Daily. Now let's get on to this episode. Ozgun Erdogan is the founder of Citus Data, a company building scalable PostgreSQL. Ozgun, welcome to Software Engineering Daily.
Hey, it's exciting to be here.
Let's start with some history. 10 years ago, the types of databases that we had and the types of workloads that we were doing were simpler. Yes. What did the database landscape look like a decade ago?
I think, as you put it, it was much simpler and much more uniform a decade ago. And specifically, I can speak to my experiences at Amazon as I was working with these databases maybe 7-8 years ago. If you rewind back maybe 15-20 years, Amazon started out as this website, and then that had a database in the background, and then that database was Oracle. And over time, as Amazon switched over to a service-oriented architecture, other databases started coming into the picture. There was MySQL, there was BDBs, Berkeley databases, and Dynamo was a system, a distributed database that Amazon built in-house to address some of those workloads. And this was on the operational side of things. So you have your website, and then your website serves requests to the customers. There's a second part to this picture, which is your customers are coming in, they're doing stuff, they're buying books, they're buying videos, and then you capture that data, you want to look at that data, you want to analyze that data, and that was a completely separate pipeline as well that was initially on relational databases, and over time that changed too. And it became more and more complex, more and more databases, and it evolved that way.
So certainly it got more complex, but 10 years ago, we kind of had these simpler sets of workloads, and we could divide these types of workloads into OLTP and OLAP. And OLTP means the simple create, read, update delete operations we do with a database, and OLAP would be the big data warehousing analytic jobs that run across large volumes of data. Is that an accurate description for the two broad types of workloads that we had about a decade ago?
I think there is also on the OLTP side a workload that's more transactional, like that involves distributed transactions. So if you look into finance, so that still goes into OLTP as a subset of OLTP, more on, hey, I'm a bank and I need to process your bank account and my bank account. And when you give me money, when you send me money, then that needs to be a transaction and an all or nothing operation. That's slightly more complex than the operational workloads, but I think that's an accurate description.
I see. So you're talking about atomized, distributed transactions.
Yes.
Okay. So do these types of workloads still define all of the types of database workloads that we have today?
I don't think they do. I'm looking at it in two dimensions. When I think of workloads, I always think of them as one, how does the data change? How did the data change? And then two, how did the computations, the operations that you want to do with that data change? And on the data side, I think one, data became much bigger. So it became tremendous. It changed that way. And we're now recording and capturing more and more data. And also it became richer in the process. So 10 years ago, it was you normalize that data, you put into columns. These days, you have semi-structured data, you have log data, you have many different types of records. So data changed a lot in the past 10 years, certainly, and it's very different than it was a decade ago.
So as our data has gotten richer and the types of transactions we're doing have changed, one way that we've been solving this problem is by using a much wider variety of databases. Mm-hmm. Why is that our solution? Why is our solution to no longer, there's that famous phrase by Michael Stonebreaker, the age of one size fits all is over. Mm-hmm. Why are we starting to use a wider variety of databases?
I think part of it is that databases, if you tweak them for specialized workloads, they become much more powerful. I think that's one part, and that's always been there. And databases initially started out in 70s as doing your OLTP workloads, and over time they added the OLAP data warehousing workloads. The other part of it is with scale, databases evolved into distributed databases. And then when you look at distributed systems, obviously the trade-offs you're making on the OLTP side and the trade-offs you're making on the OLAP data warehousing side are different. And I do expect for them to reconcile over time into not many databases, but into fewer databases. But as things stand today, you're not there.
So as we've expanded into this taxonomy of different databases, we are starting to get a better picture of what these trade-offs are that we are exploring as we go from Cassandra to Riak to Postgres to whatever else. What are these types of trade-offs that developers are making when they go with these different types of distributed databases? Why is one database better than another database at OLAP or OLTP?
For OLAP and OLTP specifically, I think for OLTP, what you're looking to do is you have high throughput writes into your system. Like you have hundreds of thousands of writes coming into your system, and you have low latency requirements. And the primary challenge there is when you're updating the data in such large volumes, how do you keep distributed data consistent? So for OLTP, data consistency becomes a key challenge. And how do you ensure that when you have failures, when machines or the network is failing left and right? So that's the primary challenge for OLTP. For data warehousing, where the data is more events data, where it's immutable data, or where it's append-only data, you can load them into your system, and what you're looking to do is, okay, I'm running this query on my system. How do I effectively parallelize that query? How do I make sure that the data, like the network, doesn't become the bottleneck? And so that's a different, like how do I take a computation, break that computation into smaller pieces, and how do I execute it in the most effective form? And that's a different challenge than, hey, I care about data consistency. How do I keep this data consistent?
What are the problems that emerge? Okay, obviously there are these different trade-offs that you just highlighted that we can explore with these different databases. Why is it problematic to solve this approach with a variety of databases? Why is consolidation desirable?
I think it comes down to simplicity or usability or maintainability. So if you have 10 different databases within your system, and if you have to integrate all of those databases together in order to solve your problem, that obviously is harder to set up and harder to maintain over time than if you have one or two or three different breeds of databases that you understand. So it's a complexity problem. It becomes a complexity problem. And to give maybe one example, I'm thinking out loud here. Let's say you want to capture real-time, near real-time analytics out of your system. So there's all this data coming in, and your user data lives in Oracle, your log data goes to Hadoop, and then maybe out of Hadoop you do MapReduce or Spark these days to take that and put that into a NoSQL solution, and then you capture some of it from your relational database, say this is Oracle, and then you reconcile that in a NoSQL solution. That's a lot of work for the developer and a lot of work for the database administrator to understand, to couple them together, because all of these systems speak different languages, and then it becomes challenging.
And so as you see this multiplicity of different databases, you have started to question whether developers really need so many databases. And from your point of view, PostgreSQL is sufficient. And this insight is why you eventually started Citus Data. So before we get into the scalability details of PostgreSQL, could you give a quick explanation for what Postgres is for people who have never worked with it or they're not database experts? What is Postgres? How does it compare to other SQL compliant languages like MySQL?
So I'll answer that question maybe in two forms. One is PostgreSQL sufficient, and can it be sufficient for different workloads? And to be frank, when we started this, we didn't go into it thinking PostgreSQL would be sufficient for all workloads, like very openly. That's something PostgreSQL has grown into with these past releases, like with the extension APIs. And when we started, we practically looked at feature-rich and powerful databases, MySQL and PostgreSQL to be specific, and there were two things there. We looked at the code bases for MySQL and PostgreSQL, and the philosophy that PostgreSQL followed aligned much more with our thinking. Let me frame it that way. The decisions they made and the fact that it was a robust, well-thought-out and well-designed database, it aligned with our philosophy as well. The second part, and I won't be dismissive about that part too, was that MySQL was acquired by Oracle, and if you're building a database on top of another database, that's an important consideration. So that's how we started with PostgreSQL, and over time PostgreSQL evolved over the past years as well to be really sufficient for many, many workloads.
So explain why PostgreSQL today solves all of the database needs that we have been discussing. Why did the ecosystem grow into something that was powerful enough to solve all of these use cases?
I don't think it solves them today. And to be frank, I don't think it's the best database in the world either. I think it could be. And the reason for that is PostgreSQL has been forked as a database dozens of times. So if you search around, if you look around, there are dozens of commercial databases, dozens of specialized databases that have been successful, that started with the PostgreSQL code base and that forked from it. So it is certainly, now what happened in the past couple of years is, and it might have been that PostgreSQL has been forked one too many times, is that the PostgreSQL community has started thinking, okay, people keep doing this. They start with PostgreSQL, say PostgreSQL as of 8.0 or version 8.1. They fork it, and then they go and build their own thing. And as they do that, they lose out on the newer features that come into PostgreSQL, and they also lose out on the PostgreSQL community side. So what can we do to make sure that it doesn't get forked, at least not as much? And they introduce these extension APIs, and these are ways to extend the underlying database to build your own database or to make it more powerful. So an extension is a way to enhance PostgreSQL's ability in a structured way.
So the importance of the extension, if I understand it right, is that if you want to build your own version of Postgres, you can't fork it. Because if you fork Postgres and you start writing your own version on top of that fork, then you're deviating from the open source community. And this is like, forking Linux and expecting to get the best of the evolving Linux ecosystem. You simply can't. You lose the ecosystem that is constantly evolving if you fork it. So what Citus does is uses a Postgres extension. And you're saying that this is a recent development. You just explained what a database extension is. So tell me more. Tell me if that's accurate, and tell me what Citus Data's extension does.
That's exactly accurate. And in terms of forking from the database, that observation is exactly accurate too. When you fork and when you deviate, then you are losing out on the community. And not only that, you're losing out on new features that come into PostgreSQL. So for example, Postgres 9.4 had the JSONB data type. And when our customers asked us, when can I use JSONB? The answer was today. You don't need to do anything different. This is an extension, so we just pick it up. So you lose on not only on the community side, but the new features that come onto PostgreSQL. To answer your other question on Citus as an extension, PostgreSQL actually has many extensions. I would say in the hundreds. Citus is probably the one extension, the first extension that makes PostgreSQL a distributed database, that extends it with distributed functionality. And what Citus does is Citus uses more of these extension APIs, maybe different than what some of the other extensions do, like which enhance it with, let's say, not as much functionality, but they don't need to use as much of the extension APIs either.
So as a naive question, explain what are the challenges of scaling a database to where it becomes distributed?
And my counter question would be for what type of workload?
Let's just talk broadly. Like, what are the things that become... So our database gets so big that we need to scale it to multiple nodes. What are the problems for people who are unfamiliar with the concept of distributed databases? What are the challenges that you will begin to encounter, whether we're talking about read workloads or write workloads or anything, just the general challenges of distributed databases?
Got it. And I'll talk about it in two ways. One as the person who's migrating from a single node database to a distributed database. I think as a user, what are the challenges I should expect? And then the second part is as someone developing a distributed databases, what are the challenges? And then what are the general challenges in building a distributed database? And what are the challenges that relate to using the extension APIs? So I think if I rewind it all the way back, as a user, the primary challenge is one of expectations. We have a lot of people who come to us, who talk to us, and I am grouped them into two camps, although it's not a strict 0 or 1. One is I've been using PostgreSQL for the past 5 years. I have 10,000 database tables, and when I switch over to Citus, it will just scale. Like, that's the expectation that people have. And I think it's on us to communicate more and say, hey, actually, it's really hard if you are sticking to your existing data model and if you are looking to use all of the existing features to just scale that out. Like, because I think the data model and the type of functionality you're looking to do, there is more that we need to do in communicating, okay, this is how you would think about modeling your data, this is how you would think about sharding your data, and this is what you need to do more. There is a second group who are thinking about it as, hey, I'm going to build a big data application. And I have some affinity, or I like PostgreSQL, or I've been using it for the past year or so. And there, I think it's realigned more just because of the expectations there, because your then second best alternative is just to denormalize the entire thing into a table or have multiple tables modeled that way. And Citus offers a more powerful framework by virtue of leveraging PostgreSQL. So as a user, I think it's the expectations that you're coming into the system. And one good thing about extending PostgreSQL is that we provide all this functionality. Another drawback is that people come with the same expectations that they have built on PostgreSQL, and when they expect that as they're scaling it out, those expectations no longer hold. And that's an area where we need to communicate more. If you're looking to do this, then here are the 2 or 3 alternative data models that you can go with. So that's on the user side. How do I think about distributed systems in general, distributed databases in general, and align those expectations?
So one aspect of the scaling challenge is that as we get these multi-node, 5, 10, 100 node databases, is that we need to be able to scale how we query these databases. And if I understand correctly, I'm not a distributed database expert, but network I/O is a big bottleneck, and you want to make your distributed queries work in a way that minimizes network I/O. So maybe you can tell me if that's true, to what degree it's true, and how do distributed queries typically work in Postgres? If we're not talking about Citus Data, how does a distributed query typically work in Postgres, and how does it minimize network I/O?
So in Citus itself, and that is true, if you think of it as network I/O, and the thing about network I/O is it has 2 dimensions to it. One is the latency, the other part is the throughput. And your throughput from the network I/O is fixed. So you have 2 machines there on the network. You have a 1 gigabit or a 10 gigabit network. You have 10, you still have a 10 gigabit network. You have 100, you still have a 10 gigabit network. So you can throw more CPU, more disk into the problem, and that will scale. But network isn't as easy to scale, particularly as you're adding new machines into the cluster. You're still bound and bottlenecked by the same throughput in your cluster. And if you look at it on the read side, on the hey, I want to parallelize my computation side, is then what you're looking to do is you can solve that in 2 ways. You can solve any distributed systems problem in one of 2 ways. One is you pull all the data to your computation. So the other way is you take your computation and you push your computation to your data. And as an example, let's say you have your events tables. You have events for this year, events for the past year, events for 2 years ago. A query comes into your system, you can effectively pull all that data into a single machine and do your computation on that machine, but obviously that doesn't scale. The other thing you can do is you take your computation and transform that computation in such a way that you can push it over to those events tables, execute them there locally, and only do a final computation to get the results. And what becomes challenging is how do I take one computation or any computation and express it in a way where it can be pushed down to where the data is.
Okay, so how does normal Postgres handle this type of... So with the distributed query, you want to break up the distributed query in a way that brings that computation to the data. How does Postgres typically do that? And what are the improvements that you make with Citus?
So PostgreSQL currently doesn't do that. PostgreSQL is very powerful on a single machine. So it doesn't go through the step of, hey, I need to distribute this, I need to plan this for the network I/O. It's Citus that extends PostgreSQL to do this. Essentially, when you send a query to Citus/Postgres, Citus says, okay, this is a distributed table, this is my distributed table, so I'm going to replan this query for distributed execution, and I'm going to break this query up into smaller pieces, and then I'm going to push it to the data, and we cooperate with the PostgreSQL planner executor quite a lot. Then again, all of that logic lives within Citus. It's not in PostgreSQL there today.
So is it open source?
Yes, Citus is open source as of a couple of months ago, and then you can go to GitHub, search for Citus, C-I-T-U-S, and then you'll see the Citus project and how we do all of these things within the GitHub repo.
Okay, so if Postgres is going to be the one database we use for everything, and I'm using the Citus extension in order to have distributed query functionality, I need to be prepared for write-heavy workloads as well as read-heavy workloads. How does the Citus extension handle these different types of workloads?
So right now, the Citus 5.0 and then the 5.1 extension, which is the version that we recently open sourced, is tailored towards more read workloads. So you're ingesting your data either in small batches, or you're ingesting data where you're like scaling to 50,000 inserts per second, maybe a bit more. And we do that through Citus as a metadata server, a single metadata server that you talk to as you're ingesting your data into it. And then that metadata server knows where the shards are and tells you where to route your queries. So that's the current architecture. We are doing work today, and I'm actually happy to pre-announce it, let's say, in this podcast for the very first time, where we're also thinking, okay, for the write-heavy workloads, for the operational workloads, how do we go about removing the single authoritative metadata server? And upcoming Citus releases will introduce new functionality where your writes won't have to communicate to a single metadata server, but then they will be able to go through any one of the nodes in the cluster. So that's upcoming work, and I'm pre-announcing it for the first time, where you'll be able to talk to any node in the cluster, and then your writes will be routed and then executed through any one of those nodes.
Okay, that's awesome breaking news for Software Engineering Daily listeners. This episode of Software Engineering Daily is sponsored by Braintree Payments. Mobile app development can be complex, but integrating your payments no longer has to be complex. With Braintree, your business can accept nearly every type of payment from any device with just one integration. Learn more at braintreepayments.com/SEDaily. Braintree's API supports Android, iOS, JavaScript, and many other languages. The documentation for Braintree is clear and elegant, and if you're integrating payments into your app for the first time, you can call Braintree's customer service and get assistance with your integration. Don't get frustrated when you're trying to integrate payments and monetization into your app. Go to braintreepayments.com/SEDaily and monetize your app today. braintreepayments.com/SEDaily. Now let's get on with this episode of Software Engineering Daily. Thanks for listening. So you mentioned this metadata server. Mm-hmm. Could you give me some more context for how that works and what are the responsibilities? Like, where does this metadata server sit? What does it have to know? Is it like a master node? Does it have to perform some kind of consensus with other nodes? Give me some detail on how the distributed systems architecture works around that metadata server.
Sure, absolutely. And as a quick clarification, the metadata server and all the other servers in the system are regular PostgreSQL instances that have the Citus extension loaded. The metadata server currently is the server that you talk to, where you create your tables and you say, okay, I'm going to designate this table as a distributed table, and then this is what I'm going to shard on. And at that point, it becomes the metadata server where that keeps the shard placement information and statistics. That way, when a query comes into the system, that metadata server, or you can think of it as the master node, can look at those statistics, can efficiently break down queries into many smaller pieces, push them down to the other nodes in the cluster and execute them. So it basically is the authoritative node on keeping the metadata, and you can replicate that metadata to the other nodes, but then it goes back into the right workloads where you have consistency challenges. How do I make sure that that metadata is consistent? And then that's the area that we're looking to improve on, that we're looking to make available in the product in upcoming releases.
So can you take me through the failure scenarios? I guess first, what happens if just some random node, database node fails? And what happens if the node with the metadata server fails?
Yep. So if some random node fails, then Citus will take care of that automatically. And statistically speaking, that's much likelier to happen. And I'll relate to the, say, on the data warehousing side, the Hadoop example. Hadoop had a single name node and a single task tracker for a long while. Because if you have 100 machines, chances are any one of the 99 machines are going to fail are higher than this particular server is going to fail. So when a worker node in the current Citus architecture fails, Citus automatically realizes, okay, this node has failed, and then it will do failovers for those queries, and then it will even do mid-query failovers. So if you have a query running, and if parts of the query are failing, then it will automatically reroute that work to the other worker nodes. If the metadata server fails, our customers currently have a streaming replica of that metadata server, or on the cloud, some choose to back it by EBS. Depending on what you do, you either fail over to the streaming replica secondary, or you spin up a new metadata server that has that small metadata. That's how you handle it today.
Okay, got it. I want to expand the context of the conversation by talking about a customer example. So one customer example I've seen you talk about is a company called Cloudflare. Mm-hmm. Explain what Cloudflare does and how they use Citus Data.
Sure. Cloudflare is a content delivery network where you can think of them as your content when you're serving these websites. They sit as front edges, and then they cache your content and they deliver it to different geographies. And I think more than 5% of the internet's traffic flows across Cloudflare. Obviously, when they're doing all these routing and then all these caching requests, they capture a lot of data that relates to, okay, who hit which website, how many requests came in for that website as raw events data. And today, they take those events data, I think it's 400 terabytes compressed per day, and then they put it into Citus. They lightly aggregate that data within Citus, and the end results are, if you think of as like 2 million websites that are powered by Cloudflare, is like on a website by website basis, how many people hit Cloudflare, how many distinct IPs hit this particular website, how many distinct IPs hit this particular website over the past minute, past 5 minutes, past 15 minutes, what are the top IPs that visited this website or that attacked that website. So they put all that events data into Citus and aggregate it within Citus, and they provide those insights as dashboards to their end users, so that if you're powering your website through Cloudflare, we can go over to that dashboard, look at the different people who visited that dashboard, who visited our website, the different IPs that visited the top IPs, the distinct number of people coming in. So Citus powers that real-time dashboard in the context of Cloudflare.
So how would Cloudflare's architecture be different if they were trying to do this through, I guess they would not be able to do this through regular Postgres. So what would they be using if they were not using Citus?
I think initially they built the initial version of this product on PostgreSQL itself. And then it just got to a point where the initial solution just didn't scale. And that's why we talked to them. They're like, we already know Postgres. We like PostgreSQL quite a lot. And then we rely on functionality on PostgreSQL. How do we make that scale? And through using Citus, and Citus is PostgreSQL, they were able to get this rolling and deployed within 2 months for the volumes of data that they have, which is quite impressive. Essentially, one engineer sat down and then looked into, okay, how do we scale that out? And usually those projects take a long time, particularly when you go into production, when you plug in these dashboards. In this case, it was, okay, this functionality, this is how we model the tables. And then from start to finish deployment, it was fairly quick, and they scaled out PostgreSQL for their use case.
People have been using Postgres for a very long time, and obviously people have been doing ad hoc scaling. What are the techniques that people typically have used in the past before Citus built this, more formalized way of doing scalability? What were the techniques that people were using?
I think the primary technique that people were using is doing application level sharding. If you love PostgreSQL, and quite a few people do, and then if you want to stay on PostgreSQL, then you need to manage the sharding and then the replication and the failover and the data consistency. And if you're looking to do query parallelization, then the query parallelization yourself. And typically people don't go all that way. So what they do is they think, okay, I'm going to shard my database, my tables myself, and I'm going to shard it on this particular dimension. This could be user ID, this could be application ID, this could be zone ID, this could be customer ID, and I'll do all this logic on the client side So my client that talks to the database will know how the underlying tables are sharded and represented. And when they query, I will build custom logic to route these requests, and I will build my own logic to do replication and my own logic to do failover. So I think that's the primary thing that people do with PostgreSQL, that people did with PostgreSQL.
I want to ask you about the broader database ecosystem, because we've done some shows on databases that fall under the label NewSQL. Mm-hmm. Sometimes these are databases that describe themselves as NewSQL. Sometimes, this has just been slapped onto them, whether the database is CockroachDB or MemSQL or VoltDB. Mm-hmm. Each of these databases is trying to provide the performance that NoSQL has for OLTP, but also provide the ACID guarantees of a traditional database. What do you think of this term NewSQL, and what do you think of these databases?
I think they're all good databases, and I think what we're looking to do together is to take the SQL database and move it to a place where the world is simpler, the world is easier, and then what databases did really well, or let's call it SQL databases did really well on a single machine, they can also do really well at scale. Now, there are different ways to go about this, and I'm part of Citus, so I'll be biased, like my technical opinions are biased. At a higher level, we'll always be biased. At a higher level, you can either build that database from scratch, or you can take an awesome database, it used to be, and then you fork from it. And I think as of a couple of years ago, there is a third way, which is, okay, it doesn't have to be these two ways. PostgreSQL is a very, very powerful database that's becoming more powerful by the day. And then it now has these extension APIs. So instead of following these two approaches, you can take it and you can extend it. And Citus as a database is following the third newer approach, where we're not building it from scratch, because to be honest, PostgreSQL is awesome. And then it's been around, like people have been working on it for like more than a decade. And we're saying, can we leverage the power of this awesome database and all the features that it has and make PostgreSQL become the distributed NewSQL database through these extension APIs? So I think that's how it's different. And then obviously the second part of it is, by virtue of leveraging these extension APIs and being close to the PostgreSQL community, is the question of open source. So we started out as a proprietary database, but as we leverage these extension APIs and as we had these customers like coming in and then using Citus, deploying it in production, the question that we received was, okay, PostgreSQL is open source, and when I think of you guys and when I think of my workflow, I'm always thinking about open source. And then that's why, as of I think a month and a half ago, we open sourced the core of Citus and the extensions to both like aligned with PostgreSQL at that level, and also to show that this is possible as an extension through the PostgreSQL extension APIs.
Are there situations where you would say that MemSQL or VoltDB or CockroachDB, would you ever say that these are a better fit than Citus DB?
I don't know.
Or Citus Data, sorry.
Yeah, I don't know enough about each specific database to answer that question at that level. I can answer it in two ways, and I will answer it in two ways. One is, if I look into the PostgreSQL extension APIs, because they define what you can extend today, I will say, what can I extend and what can't I extend today? Because these APIs, there is a new one with each release. And today, you can extend a lot in PostgreSQL. You can extend the write-ahead logs, you can extend the replication, like the logical replication system, you can write your own indexes, you can write your own data types, you can extend the planner, the executor. The two things you can't extend today are, one is the transaction manager, and then the transaction manager in the context of distributed transactions. So going back to the earlier use case where I said you start a transaction and then in a financial application context, say we're both Wells Fargo customers or like Bank of America customers, and your account lives on one machine, so that's like a commit, and then my account is another machine, that's another commit, and then we commit the entire thing, the entire transaction. So the transaction manager APIs are sufficient if you're doing transactions within the context of a single machine. If you're looking to do transactions, distributed transactions that span across multiple shards, that's still being debated, like within the PostgreSQL community. How do we provide the API so that it enables PostgreSQL to be extended for those type of workloads? And that will come out, but it's not there in the extension APIs as of today. So that's one area. The other part that's not extensible is the parser, because if you extend the parser, this is the SQL query parser that comes into the system, then there may be conflicts. Say my extension extends it in a particular way, another extends it in another way. How does PostgreSQL ensure that the two grammars don't conflict with each other? Postgres offers two ways to work around this. One is through user-defined functions, which is what Citus does. You can express what you want to do by leveraging user-defined functions. And another thing is Postgres has this with clause present in like many of these SQL commands that you can extend where it doesn't do checking. So that's the second way it offers it. So at a technical level, if you're looking to do something way fancier on the parsing side, which I haven't run into personally, or if you're looking to do distributed transactions, the extension APIs are evolving to meet that need. From a use case standpoint, Citus works best when you're looking to ingest large volumes of data and when you're looking to run queries that run in under a second, not large data warehousing workloads, not large data ETL, but hey, I have a query and I want this query to run in a second, those near real-time, human real-time workloads. And if you expand beyond that, if you're looking into, say, data warehousing, that's not a good fit. It's almost like you're looking to extend, and that's from a use case standpoint.
Are there any verticals where you would say like maybe it would make sense for more specialized databases for users to use? So I don't know if there's a company, maybe they need a lot of geospatial data or time series data. I mean, there are these contexts, or like a graph database. There are these contexts where the domain specific requirements for how you can store that data, they can really inform your data access patterns, or they can make your data access patterns better. I mean, would these be conceivable scenarios where you would say, yeah, okay, it would make sense for somebody to go with one of these domain specific databases, either in, augmenting their Postgres database or in place of their Postgres database?
Yeah, that's a really good question. For time series databases, I would say that's how people are using Citus to a certain extent today. They have these time series data or events data coming in, and then they're looking to gather insights quickly out of that data. So that's a use case that Citus does at scale today. You can augment on that to build your own data types or functions to gather more insights or quicker insights out of time series data. So if you're looking to do, say, funnel queries, and that's possible within the extension framework. For geospatial data, there is another very powerful PostgreSQL extension called PostGIS, where it extends PostgreSQL with geometries, with raster objects. So it introduces these new data types that make sense in the context of geospatial, and it also adds indexes, functions, aggregate functions to power those. So, and PostGIS as a community is growing. I think it's in deployment in thousands of production sites, if not tens of thousands. So that I think there's already an extension that does that in the context of extending PostgreSQL. For graph databases, I don't know enough about them to say one way or the other. One thing I could say, and I think that's what we're saying with the Citus extension, is it makes sense to have specialized databases for sure, because the workloads are very diverse, the data is very diverse. But if you're building that specialized database, why not look at PostgreSQL and the PostgreSQL extension APIs for building that specialized database?
Okay. Well, so as we're talking about these other databases, the elephant in the room for many years has been Oracle. I feel like Oracle is this, I've only been in the programming world for like 6 or 7 years, and I feel like when I was entering the programming world, Oracle was, I don't want to say it's been fading, but I don't think of Oracle as I don't know. I haven't done any shows on Oracle. I haven't heard any demand for hearing about shows about Oracle. And yet Oracle is still this massively popular database. It's deployed everywhere around the world. How does Oracle fit into the modern world? And is the current state of Oracle, is it just the byproduct of how long-lasting the lock-in of a proprietary database is?
That's a hard question to answer. I think the state of Oracle is they were and they are pretty successful if you look at it from a revenue standpoint. So there are different types of companies, different types of enterprises, and Oracle is a pretty good database. I'll say that. I think it's not where it fails, and why we don't hear so much about it is that it fails to reach to the developers. And part of it is being a proprietary database, as part of it is cost. Because you can't just go and git clone Oracle as a database, and then it's not built for that. The business model is not built around it. And I think those two things, with these changes in the past decade, like as more Oracle hasn't caught up, not to developers, and that's why we're not hearing about it. That said, I think if you look at the database landscape in terms of revenues, Oracle is still the big player in the market, like by far, and that will change over time. I think it's, but I think they're also a really good database. I don't think it's necessarily on the technical side. As someone who's looked into Oracle, it's more on the being the proprietary database, not being cost effective enough, and not plugging into these new languages and then new workflows enough, that we're not hearing about it as much on the developer side.
Since we're talking about business models here, tell me about the business model of Citus Data.
The business model is an open core model. Citus is open source, it's available, and you can download it and you can actually put it into production. We have customers who put it into production there. If you are a bigger company or if you're an enterprise, you need certain additional features, then Citus also has an enterprise edition that provides you that functionality, and then also help and support and services that come along with it.
So databases are obviously mission critical to a company. It can be really hard to sell a database to a first customer. Mm-hmm. How did you make that first sale?
That we didn't think about it as in the context of making the first sale. What we did was we went and had this deployed and sold this brute force by virtually talking to everyone and going with everyone who was interested. And after I think about a dozen customers or so, we said, okay, we stopped and we looked back and said, okay, these people who are using us, who deployed us in production, why are they using us? So it went more as in, let's go and talk to everyone, let's go and get it deployed anywhere we can. And after some time, we stopped and we looked back. And when we looked back, the people who were using us, the people who were deploying us, and the people who were paying for Citus, they did it because they loved PostgreSQL. And then they looked to scale out PostgreSQL, this database that they already trust, that already keeps their data in a scalable manner. And that's when we realized, okay, actually people who use Citus are looking to combine the trust, the reliability, and the functionality, the feature set, the evolving feature set of PostgreSQL with scale. And then that's how we looked into it, and that's how Citus has been growing. And that's more or less how it happened.
When you look at the broader distributed systems community today, what are the projects and the companies that are most exciting to you?
That's a hard question to answer too. I've been in the database space for quite a while, looking really deep into the database space. To take a step back and look at it as a holistic, like in a holistic form, I can say in the data space, one trend that's happening, we talked about OLTP and we talked about data warehousing. There is a new type of workload that's emerging on the machine learning, data mining, and AI side. So that I think is exciting as a development. I think there are also these technologies that enable deploying, packaging software together. There's Docker, there's Mesos, those technologies as well. What's really exciting to me, and I don't see, and maybe we'll get to this, is making databases more usable. Like if you look into how you build applications today, they evolve quite a bit. With databases, you're still using SQL, you're still connecting to it. I wish there was a way where I could just talk to my database, where I say, hey, my database would ask me, hey, Ozgun, how can I help you today? And I would talk to it more on the usability side. I know it's like far out there, but that would really excite me. Now, not only making it scale, making it easier to use, but like making it so trivial to use where I don't need to think about the underlying database or the specifics, where I can have a conversation with my database. That would really excite me.
Did you look at Parse at all when that was still around, that backend as a service company?
I know of Parse, and then they were also a Y Combinator company. Yes, I know of them, but I haven't had a chance to look into what they were doing at depth.
Yeah, I don't know much about them either, but what you were describing, the highly usable database backend experience sounds something like what they were trying to achieve. But so you mentioned machine learning, and obviously we're drawing to a close in this conversation, so I don't want to open a can of worms, but what are Google is obviously, they're going to do TensorFlow. They're doing TensorFlow as a service. I'm sure machine learning is going to be increasingly commoditized. Everyone's going to have access to it, whether they know much about machine learning or not. But what are the types of database workloads? Like, how does it change how we architect a database if we're doing machine learning all the time?
I think it's a different type of workflow where you have big data and then you iterate on that data. You make this iterative workload, you iterate on that data quite fast. I don't think the database, and at least in the way we think of SQL databases, are being built or extended for those workloads yet. I think that's going into Hadoop. That's going, like right now, Spark is looking into it. So, and over time, as that becomes a bigger space, databases will start thinking, okay, how can we do iterative workloads? How can we enable these workloads too? In the land of databases, I think that's still R, how I would use R, how I would analyze that data. And I expect that to change over time.
All right, fascinating. Well, that sounds like a great place to close off. Ozgun, thanks for coming on the show. This has been a great conversation about databases and Postgres, and I'm really excited about where you guys are going with Citus.
Sure, absolutely. And thanks for having me in the call.